Okay, so I said in the video on when we talked about change in enthalpy and bond energies that there was a more accurate way to determine the change in enthalpy. And so we want to talk in this video about enthalpy change and Hess's law. We want to introduce you to Hess's law. The reason bond energies is not the most accurate way is because bond energies, the bond energy values that we have, they do not take the phase of a substance into account. Hess's law does. So let's talk about that a little bit. First, in order to discuss Hess's law, we need to understand the definition of a state function. Okay, so a state function, by definition, is a property that is independent of path. What do we mean by that? I think one of the best analogies is think about taking a trip somewhere. So let's say we're going to go to the Grand Canyon. All right, we're going from Georgia to the Grand Canyon, and we could take back roads. We could take the scenic route. Right, it's going to take us longer, but we'll see more cool things. We could take interstates. It'll be probably mostly boring, but we'll get there faster. We could get there even faster by hopping on an airplane and flying over there and renting a car and then driving the rest of the distance to the Grand Canyon. Now, each of those three trips, they're going to be different as far as the amount of time involved. They're going to be different as far as the actual mileage traveled. But the end result's going to be the same, right? You still end up at the edge of the Grand Canyon in amazing wonder of what God's created. So the end result's the same. And so that trip in that sense is a state function, right? You started off from a point and you ended up at another point. When you're just looking at going from here to there, the end result is the same, right? And so when we talk about Hess's law, we're referring to Germain Hess, who in 1840 said a chemical reaction, when it comes to its change in enthalpy, is like that. The change in enthalpy is the same regardless of which path you take. Change in enthalpy is a state function, right? So as long as you start off with the same reactants and you end with the same products, it doesn't matter how you get there, right? It may be a longer reaction, there may be more steps or fewer steps involved depending on how you do it, but if the starting point is the same and the end result is the same, change in H is a state function, all right? And so that was an important point. So let's look at a particular reaction. Oops, the combustion of methane, okay? And so that is, write this down, that's CH4 as a gas plus 2O2 as a gas yields CO2 as a gas plus 2H2O as a gas, all right? So here's our reaction for the combustion of methane. And so we could just have this reaction exactly like it's listed here, and we could calculate the change in H, or we could take a few extra steps. Let's say instead of doing it like this, let's say we start here, but then we break these compounds down into the individual elements, right? So we break this down into carbon and hydrogen. This is already oxygen. And then we have another reaction where we form on the other side from these elements as they're broken down, we form carbon dioxide and H2O. So we took more steps, but the end result was the same, right? We started off with this, we ended up with this. Well, the change in H would be the same for that second longer reaction as it was for the first shorter reaction, this one here, right? Because again, change in H, change in enthalpy is a state function. And so as it turns out, we can use a table like that on page 424, which has a list of standard enthalpies of formation. You'll notice in that table there that those values are listed as change in H, F, with a little degree symbol up top here. All right, so the reason that's written that way is because this stands for the change in enthalpy of formation, that's what the F is for, at 25 degrees Celsius or 298.15 Kelvin. And that's the reason that temperature is chosen is because that's room temperature, right? And so this is the change in enthalpy of formation at room temperature for these various compounds. And so if you have a formation chemical function, right, that forms that compound, then that's the change in H for that formation. Now, the opposite of formation is decomposition, right? So if we were to decompose, if we were to break that compound down into its individual elements, then the change in H for the breaking down of that element would be the exact same value, but it would be, as far as the sign goes, it would be the opposite, right? So if it's negative there, it would be positive when you break it down. If it's positive for formation, then it would be negative when you decompose it, okay? So that's one thing that we need to understand regarding that chart. The other thing we need to understand before we can talk about Hess's law is this. We need to know one more important point, and that is that the change in H of formation of any element, and this is an important point right here, in its natural phase, all right, is 0. All right, so make sure that you remember that. The change in enthalpy of formation of any element in its natural phase is 0. So for example, in our equation right here, oxygen at room temperature appears exactly like that, right? It's just O2 in gas phase. That's what's floating all around us in the air. So the change in H for this substance in this equation would just be 0, right? So given that point, understanding that we have these tables of the standard enthalpies of formation, then I can give you Hess's law and we can actually do a couple of problems. And so Hess's law, simple mathematical representation of Hess's law would be this. For the reaction little a plus little b. So in other words, on the reactant side, we have some compound capital A, and the number of moles, or the stoichiometric coefficient, is little a for that compound. The coefficient for compound capital B is little b, right? And that produces little c, capital C, plus little d, capital D. And of course, we could have more compounds in the reaction. But for a reaction like this, we can say then, based on Hess's law, this is Hess's law right here. Right? And make sure you know this. Change in H is going to be equal to this coefficient on the product side, little c, of the change in enthalpy of formation of the capital C compound, that's a capital C there, right, plus little d of the change in HF for the capital D compound, minus little a change in HF of capital A, minus little b change in HF for capital substance capital B. Okay? All right, so let's just make sure we talk through this and make sure we understand this equation, all right? You need to know this equation. You're going to have to memorize that, right? Hess's law. And so basically what this is if you take the sum of the change in enthalpy of formation for the compounds that are on the product side, right, this side of our chemical equation, and you subtract from that the sum of the change in enthalpy of formation for the compounds on the reactant side, both of these are subtracted, subtraction here, then that will give you the total H for the reaction. So I just want to write it down in a slightly different fashion that he does not do in the book. But to me, this just makes an important point so that we don't get confused here. And that is that change in H, when we're using Hess's law, change in H is going to be equal to the sum. That was terrible. Write that a little clearer. If you remember, the symbol for sum is that Greek letter there. Change in H, and that's our Greek letter up there. Oh no, right here. There we go. The sigma. Change in H, little f, of the products side, right, minus the sum of the change in HF of our reactants. The reason I wanted to write it down like that, and sorry that I'm not staying straight, is because I wanted you to catch the fact that this is sort of the reverse of what we had whenever we figured out the change in H using bond energies. Because if you remember, this is Hess's law, right? Hess's law here. But when we use bond energies, we said that change in H was basically equal to the sum of the reactant bond energies minus the sum of the product bond energies. So it's like the reverse, right? So I don't want you to get those confused. I want to make sure you keep that straight in your mind. It's not a different value in the sense that we're still calculating the change in H. And when you calculate those two, the values are going to be similar, regardless of which way you do it, but they're not. But Hess's law, like I said, is going to be the more accurate of the two, because Hess's law takes phase into account, okay? And in fact, you can see that if you look at our chart on page 424, the table there, if you look at each of those compounds, you'll see that next to the compound, it lists the phase, right? For example, the third item down on the left is C6H6 in gas form, and it's got a different change in H than C6H6 does in liquid form, right? We see the same thing with water. If you look in the second column, all the way down at the bottom, the value will be different depending on the phase. So because Hess's law takes phase into account, sorry for that loud noise, I'm glad I was wearing shoes or that would have really hurt. Since Hess's law takes phase into account, it's more accurate, okay? So let's actually do a couple of problems. We'll do the ones on page 425, example 14.2. And that says, what is the change in H of the decomposition of hydrogen peroxide at 25 degrees Celsius? That just means we can use our values of the change in enthalpy of formation in our table there. So what's the change in H, and is the reaction exothermic or endothermic? Here's the reaction. 2H2O aqueous yields 2O2 hydrogen peroxide, sorry. It yields 2H2O in liquid form plus oxygen in gas form, okay? So what is the change in H based on Hess's law, right? So change in H is going to be equal to remember with Hess's law, we start with the product side. So we say we got two H2Os in liquid form. And so if we look at our table, H2O in liquid form is equal to negative 285.8 kilojoules per mole. So negative, and just to, let me put in the units so we see the units cancel out. 2 moles at negative 258.8 kilojoules per mole, right? Plus, we have 1 mole of O2, so 1 mole of O2, and O2 that's its normal phase, that's its natural phase, so it's going to be 0, right, for that guy, minus the 2 moles of H2O2, and we looked that up on our chart. H2O2 in aqueous form is going to be negative 191.2, negative 191.2 kilojoules per mole. So when we punch that in our calculator, let me just make sure I have it overlooked anything. 2, negative 258. Yeah, that's right. 1 mole, 2 moles. Okay, that looks right. And so our final value is negative 189.2 kilojoules, right? Because moles cancel out in each of those. So the other question, so there's our change in H. The other question was, is it exothermic or endothermic? Which one is it? What's that? Back of the class? Yes, exothermic. That was excellent job. I heard you from way back there. Appreciate that participation. We had this weird show whenever I was a kid where the lady would walk up to the screen and she would be like, and she would look out and she'd say, I see so-and-so, and I see Johnny, and then I see Ashley, and I see Jamie, and when she would call your name, you're like, man, she just saw me through the TV. Weird. We just kind of had one of those moments, right? Kind of gave you chills. I see Joe. I see Chandler. I see Rissa. I see Maggie. I see Will. All right, let's go to the next one, and we will be done with this video. I see Kirsten. I see Alex. I see Emily with a Y, and I see Emily with 2 E's. I see Ian. The second equation that we have here is we're trying to find the change in H of 2CO in gaseous form plus 4H2O yields 2CH4 in gas form plus 3O2 in gas form. All right, let's figure out change in H here. Again, we're going to look at our chart, and we're going to say that we have 2, I'm just going to leave off the units this time for space, 2 CH4s in gas form, and so that's going to be negative 74.9, plus 3 O2s, and we know that since that's the natural phase of oxygen, it's going to be plus 0, minus 2 COs in gas form, and so CO in gas form is going to be equal to negative 110.5, minus also 4 H2Os in gas form, and H2O in gas form is negative 241.8. So let me double check, make sure I didn't overlook anything. I see Daniel, Jackson. Those are 2 people, not 1. I see Kylie. I see Anna. Oh, Anna. There was someone else I saw. Oh, I see Kenan. And so we get a final value of change in H. Change in H is equal to 1038.4 kilojoules. And I hope I put kilojoules on my last problem. I'm second guessing myself now. I'm wondering if I just put joules. Hopefully I put kilojoules. Anyway, that's not the final answer, right? That's the answer to change in H, but they said, is it exothermic or endothermic? This one is not negative like the last one was, it's positive, and so that means that this reaction does not give off energy, it absorbs energy, so it is endothermic, all right? I think that's it for this lesson. See you guys next time. I see Jennifer. I see Carson. I see Jacob. I see Rachel. I see Jewel. I see you all.